Okay, here's a very brief review of some trigonometry concepts from the last few years. This doesn't really replace the many months that you've spent in school studying trigonometry. So it's meant to just kind of jog your memory and maybe give you a few shortcuts and tricks for working with trigonometry and solving trig equations. That will be useful in this class. Okay, so I'm going to ask you some questions along the way. If you don't mind, you might want to pause this and go grab a notebook or a piece of scratch paper or something. First, take a few minutes and try to determine the exact values of W, X, Y, and Z from these two pictures here. The triangle on the left is a 45, 45, 90, and the triangle on the right is an equilateral triangle where all the angles are 60 degrees. Okay, so pause the video, try to figure out the values of W, X, Y, and Z. Here we go, I'm going to go through it too. So if you are ready, we're going to roll here. The first thing you should notice in this first triangle is that if they're 45, 45, and 90, then these two legs have to actually be equal. So W is just 1, so that's a pretty quick one to try to solve. You just get 1 right there. Okay, now if we know that that's 1, then I can use the Pythagorean theorem. So 1 squared plus, so this side, 1 squared plus W squared, which is also 1, has to equal Z squared. And then you end up with Z is the square root of 2 if you follow that through to its conclusion. So we have all of those sides, W would be 1, and Z would be the square root of 2. And then in the other triangle, if you take an equilateral triangle and cut it down the middle, then this altitude of the triangle would cut the base in half. So Y should be half of this entire length. And since it's equiangular and equilateral, these three angles are the same, all three sides are the same, and this whole side is 2, so Y must be 1. Okay, and then if we know that Y is 1, we also know that this smaller triangle on the left is a right triangle, and we can use the Pythagorean theorem again. And in this case, it would be 1 squared plus X squared equals 2 squared. And if we follow that through to its conclusion, we'll have 1 plus X squared equals 4. Subtract 1, we have X squared, or just X equals the square root of 3. And so that's our altitude. Okay. All right, so these different side lengths will come in handy when we're simplifying exact trig values here. So we'll come back to that in a minute. Next little mini activity, take a second and just see what you remember about the graph of Y equals sine of X and the graph of Y equals cosine of X. Try to make a quick sketch of them on your own paper. Okay, if you haven't already paused it, please do, and I'm going to go through it right now. So sine of 0 is 0. I'm just going to plot a few points. If I went to pi over 2, sine of pi over 2 is 1. The sine of pi is 0. And then this is 3 pi over 2. And the sine of 3 pi over 2, or 270 degrees, is -1. And then we end up back here. The sine of 2 pi is 0. So one complete cycle of this should look like that. And then the cosine of 0 is 1. And we'll also, I'm going to add pi over 2 and 3 pi over 2. The cosine of pi over 2 would be 0. The cosine of pi would be -1. Cosine of 3 pi over 2 would be 0. And the cosine of 2 pi would be 1. So it's the one that looks like this. Forgive my sketching abilities or lack thereof. Yeah, close enough. Okay, so knowing these two graphs, kind of knowing them off the top of your head, and then also knowing how to, if you know all of these numbers in these triangles and you get used to it, that'll be much faster for you, but you can build it whenever you want it, right? You can sketch a little triangle in the margins of your paper. And if you know all of these, then you're going to be able to find, the sine of any particular angle you want. So say I want the sine of pi over 4. So here's pi over 4. I want sine of pi over 4. If you remember your SOHCAHTOA trig, sine is opposite over hypotenuse, so it would be 1 over the square root of 2. And you can, so you don't have to memorize the unit circle. You can use these, any parts of these. By the way, it probably would be important to note that this angle is half pi over 3, which is pi over 6. So if I wanted the sine of pi over 6, I would go with this angle up here, and sine is opposite, which is 1 over hypotenuse, which is 2. So the sine of pi over 6 is 1/2. Okay, so these triangles get you all those values from the unit circle that you learned maybe last year, maybe in a previous year. Okay, so what you see here are the, in these 4 diagrams, are the information that we just calculated and figured out in the previous 2 mini activities. We've also got all this information about SOHCAHTOA trig. So SOH stands for sine is opposite over hypotenuse. Ka is cosine is A, there's your A and your H. Tangent is your O and your A. So hopefully you remember this is from several years ago. And let's fill out this table. So let's go through and do the question mark ones together right now. And then as an exercise, I'll have you pause this video and try all of the other blanks. So for this first question mark, the sine of 0 degrees, I would not go to these diagrams. I would go to this graph. The sine of 0 is 0. So just sorry, quick technical issue there. So the sine of 0 is 0. And then if I wanted the next question mark down here, I want the cosine of pi over 6. So, and you can think of that as 30 degrees if you like. So in this diagram, you find pi over 6, which is here. The cosine is defined as, it's the ka in SOHCAHTOA, so it's the adjacent over hypotenuse, square root of 3 over 2. So I can write that in here, square root of 3 over 2. And let's do this next one here. So I want the tangent of pi over 4, and I can just go over to this little triangle over here. The tangent is the opposite over adjacent. It's the TOA. So it would be 1 over 1, which is just 1. That would be just 1. And then I want the sine of pi over 3. So I go and find pi over 3. And here's pi over 3. And what sine is opposite over hypotenuse. And of course, this is much faster if you memorize this stuff. But the point is, if you forget it, how do you rebuild it, right? So I go, sine of pi over 3 would be square root of 3 over 2. The next question mark down there would be the cosine of pi over 2. Now, this is an interesting thing here because pi over 2 is this 90-degree angle, but you can't use the triangles down here to define what I'm trying to do. What was it, cosine? Cosine is defined as adjacent over hypotenuse, but there's 2 adjacents. And so cosine is not defined in this triangle from this 90-degree angle. So it's much more helpful to go back up to this diagram up here. So the cosine of pi over 2 is right here. And that's, so the reason why it doesn't work in the triangle is because it's 0. And you can't have a triangle with a length of 0 or a ratio that gives you 0. The triangle would just cease to exist. So that's what's happening there. Okay, so it does have a value, 0. And then the tangent of pi. Again, using one of these diagrams is not very helpful, but it can be helpful in this problem. So you remember that tangent is defined as the sine over the cosine. Okay, so what I need to do is then find the sine of pi and the cosine of pi. And that's from these diagrams here, right? So the sine of pi is 0. And the cosine of pi is -1. So we end up with 0 over -1. Which actually is 0. Okay, so you take a minute and from this screen here, try to figure out what all of the other blanks are in this table. Okay, go ahead and pause the video. Okay, assuming you've done that, here are my answers. Hopefully this works. There we go. Okay. You were able to figure those out on your own. If you need to pause this here to take any notes, go ahead. I'm going to roll on. Okay. Another topic that comes up prior to this class is solving more complicated equations. And oftentimes you will be given an interval that you're trying to find the solutions on, because these are cyclical functions, go on forever and ever and ever and ever, and will give you an infinite number of answers, which you can describe those answers for sure. But solving this on a specific interval will give you a specific number of answers. Okay, so take a second and see what you can do with these. Pause the video right here, write them down, give them a try. Okay, assuming you've paused the video, I'm going to show the answer to the first one. Hopefully this works. There we go. Okay, let's talk about it here. So the first thing I did was move this over to the other side. So that's what I'm left with right here in light blue. Then I took the sine of 2x and made a little graph of this. Now you can think of the graph of these in your head if you want to, just kind of mentally, or you can actually sketch it out. The 2x affects the period of this function, so it's happening twice as quickly. So usually in 2 pi, sine is just one cycle, right? But since it's the sine of 2x, you get 2 complete cycles. So everything happens twice as fast is how I think of that. And if I'm trying to set this, or if I'm setting this equal to the square root of 3 over 2, the square root of 3 over 2 is a positive number. Okay, and I know that it's less than 1. 1 is the peak of this, right? You can only get sine values that are between 1 and -1. So 1 is the peak of this. Square root of 3 over 2, I'm not doing this with a calculator or anything, but I know it's got to be less than 1. It's somewhere here. So I just sketched this horizontal line at y equals the square root of 3 over 2. And it shows me visually that there are 1, 2, 3, 4 possible answers. And we're going to need to find a reference angle so we can find all of these answers. It's also worth noting that these lines right here, if I were to divide them like this, these are the different quadrants in the unit circle, right? This is quadrant number 1, this is quadrant number 2, etc. It's really, really hard to see. Let's see if I do that. This is quadrant number 1, this is quadrant number 2, this is quadrant number 3, this is quadrant 4. So that is how it would wrap around the unit circle. And you can see that there's 2 answers here, and both of these answers occur in quadrant 1. There's 2 answers here, and both of these answers occur in quadrant 3. There's lots of different ways to visualize this. And it's possible that your previous math teacher showed you a different method. Totally great. This is just one way of visualizing it, okay? So in order to find that first answer, what I'm going to do is go back to those triangles that we created and try to find something that gives me the square root of 3 over 2. You can already see the answer right there. But so that comes back to this here. I'm looking for the square root of 3 over 2. So that would either be the cosine of pi over 6 or the sine of pi over 3. And since this is the sine, so pi over 3 is the angle that we want, that will give us the ratio of square root of 3 over 2. So that first answer must be, did I write that down wrong? Oh, sorry, there's a little bit of work we got to do over here. Okay, so that answer is our reference angle, square root of 3 over 2, but it's equal to the whole inside part of this, which is 2x. It's twice whatever x is. So I have to divide by 2 to get what x is. So x itself is pi over 6. So that reference angle right there is pi over 6. Okay. Now everything here is symmetrical from these vertical yellow lines that I've drawn. So basically our first answer is pi over 6. We're good there, but there are 4 answers. The next answer comes from taking pi over 2 and subtracting pi over 6 to go backwards to that point. So if I take, did I write that down right? I've got a minus there. It looks like I need to subtract. Just a sec. Okay, sorry about that. I had the right answer here. I just wrote a plus there for some silly reason. Okay, so it's basically pi over 2, which is that value, minus subtracting backwards that pi over 6 to get to the point, which is 11 pi over 6. You just find a common denominator. Pi over 2 is 12 pi over 6. Okay, going down to the next one. If I want this value, I've got to do pi plus pi over 6 to get to that one. And then I'll have to do 3 pi over 2 minus pi over 6. And that's what I'm doing right here. You can pause this video and look at how I did common denominators. So these are all of our 4 answers. Okay, hopefully you've already tried the next one. here we go. So in this problem, this looks suspiciously like a quadratic function, right? If I let u equal the sine of x, then I've got 2u squared right there, minus 3u plus 1 equals 0, and that is a quadratic that you can factor. Each of these factors, if they're set equal to 0, then each factor is equal to 0, because 0 times any number is also 0, and 0 here times any number over there would also be 0. So either one of these things give us an equation that works. So then you solve this for u, you get u as 1/2. You solve this for u, you get u as 1. And then let's plug back in what u is equal to, the sine of x. So the sine of x equals 1/2. So then you're looking back and trying to find a place where the sine of x is 1/2. But remember, you're doing it on this interval from 0 to 2 pi. So it isn't just pi over 6. The triangle gives you pi over 6. But remember, you can visualize how to get this here is by thinking about that sine. I'll just do a little sketch of the sine. So the sine looks like this, right? And I want 5 pi over 6. So I'm looking for where it's equal to 1/2. So this is that idea that there's 2 possible answers here. And this in the middle here is pi. It's half of our cycle. So let me zoom into that because it's so tiny. So if my first answer is pi over 6, but then the second 5 pi over 6, the way I got that by taking pi and subtracting pi over 6 because it's symmetrical. Okay, so that's how I got 5 pi over 6. In the other side here, we have where sine is equal to 1, and that's right there at the tip, which is pi over 2. It's right in the middle, 0 and pi. So pi over 2 is my third answer. So there's 3 answers to this question, 2 from this factor and 1 from this factor. Okay, hopefully that jogs your memory a little bit on those kind of solving equations. Honestly, previous math classes spent a long time going over problems like this. Is a whole entire unit solving very complicated problems using trig identities and all sorts of things. So this by no means replaces all of that work. It's just to refresh your memory. Okay, here's another type of problem that you guys worked on in the past. This is more with working with angles in extended quadrants, so beyond quadrant 1. And take a second and copy this down. Again, we're on the interval from 0 to 2 pi, and see if you can find all possible answers that work for these 3 problems within that interval. Okay, hopefully you've paused and tried. My first answer, let's go into that one. I'll just zoom over there a little bit. Okay, so the cosine of x is negative square root of 3 over 2. Negative, okay, so cosine is defined as adjacent, I think I wrote that here, yeah. Adjacent over hypotenuse. And if that's true, we have a negative value for adjacent, which means I'm going backwards here. That's why this is a negative square root of 3 on the x-axis. Okay, so for cosine, you can think of it as x over r, or adjacent over hypotenuse. So this is your x value, it's going this way. So I know my 2 possible answers for this are going to be in quadrant 2 and quadrant 3. So I'm looking for this angle, and I'm also looking for this angle all the way around over here. Okay, so for this angle right here, first find the angle that's in the triangle. Use that as a reference angle and subtract that from pi. So if you go back to those triangles that we drew, those are like the root of everything, right? So go back to those triangles that we drew in your notes, or go back in this video, and you'll see that that angle right there has got to be pi over 6. We've seen that angle a bunch of times already. And if we subtract it from pi, then we get this large angle here, which is 5 pi over 6. Okay, next, if I want this angle down here, I can do pi plus pi over 6, because these 2 angles are the same. These are the same triangles, the reference angles. I think your teacher maybe called it a reference angle. I'm not sure. That's just the way that I learned it. Okay, so then you end up with 7 pi over 6. All right, let's try the next one. So same idea here, but completely different numbers involved. Now, sine is defined as, I erased my opposite. Let's see if I can erase that. Okay, it's opposite over hypotenuse. So it's kind of like y over the radius. If you think of this as like a unit circle coming around here, although it's not a unit circle because I'm using a radius of square root of 2. It's totally fine to do this. You get it right every single time. Okay, so if our circle in here has a radius of square root of 2, and my y value is -1. We can go back to those triangles and see that we're on a 45, 45, 90 triangle. So pi over 4 is our angle right here. And there's two possible answers. In quadrant 3 and in quadrant 4, y is negative. That's where our numerator here is negative. So we have this possible answer, and our reference angle is pi over 4. So I do pi plus pi over 4. Pi is half a circle. And then I get pi over 4. And then I could also do 2 pi, which is the whole circle, subtract pi over 4. And we end up with 7 pi over 4. Okay, let's talk about the cosine of x being 1/2. So here's my work for that. Cosine of x is defined as the adjacent divided by the hypotenuse. I keep erasing parts of it. All right, there we go. All right, so adjacent over hypotenuse for cosine, which is what we saw in the part A. But in this case, it's a positive. So cosine is positive in quadrants 1 and 4 because it's your x value, your adjacent. This is like the angle, the side that's next to this angle is positive. So +1 moves out this way. I have two possible answers here. I can label it with did I draw the wrong picture? Hold on a second. I got it. Okay, so it's 1/2, and I use the Pythagorean theorem to find this height, which you don't actually really need. So you can go back to your special right triangles that we drew and see that if you have a 1 and a 2, then this has to be pi over 3. So that's our reference angle. In fact, that's one of our first answers because it's already right there in quadrant 1. This one, you just do 2 pi minus pi over 3, and you get what's left is 5 pi over 3. Okay, let's try one more thing here. Another classic question is, how do you convert between degrees and radians? This is useful to know. IB will not make you do this. They'll either give you a problem in degrees or in radians. They won't make you switch between the two, but this is a topic that you've seen before, so let's see if you remember this. And I find it helpful just for my own intuition to be able to think fluidly between these two systems. Okay, so go ahead and pause this and see what you remember. Okay, if you're ready to roll, here's my answer to the first one. Basically, what I'm doing here is I'm taking my 60 degrees and I'm multiplying it by the number 1, because multiplying by 1, which is the multiplicative identity, does not change the angle, right? Pi is equal to 180 degrees. I should have a little degree symbol there. It's not written in purple. But so these degree units cancel out, and we're left with pi, and 60 divided by 180 is 1/3. So we're left with pi over 3. And you just do that same trick, okay? Every single time you can do that if you're going from degrees to radians and multiplying by pi over 180. You can multiply by 2 pi over 360 if you want to. It's just that the numbers are bigger, so why do that? Okay, now if you do 45 divided by 180, that gives you 1/4. Again, I should have had a little degree symbol there, but that's okay. So the units come out as radians. Okay, same thing on the next one. And the next one I put as an x on purpose, so you're building a little formula. So this is just describing what I just explained, right? Take your degrees, multiply by pi over 180, and then reduce your fraction and move part out. Okay, going backwards. So going backwards, I need to flip this fraction because I want to cancel out radians and leave myself with degrees. So if I do that, I've got my 3 pi over 2, which is here, and I'm going to multiply by 180 divided by pi. That's just the reciprocal of this fraction. The pi's cancel out. I like canceling out your radians, even though radians is a unitless measure. It's kind of weird, right? It's number of radiuses, radii. And then we're left with degrees, which is nice. And then you still need to simplify. So if you go 3 times 180 divided by 2, you get 270 degrees. Okay? And the last one is just a formula. Basically what I already described to you, right? Okay, so basically you got a couple choices. You can go back and memorize everything from the unit circle. There it is in all of its glory, knowing where everything is in every single quadrant. That's a lot to memorize. Or if you know those two simple triangles and know just basically what sine and cosine functions look like, you can generate all of this information whenever you want it, should you forget it. Okay? I suppose you could also, if you really wanted to get to memorizing, You can memorize all the extended trig values. This is the sine and cosine. This is all the stuff from the unit circle written out in a table. Yuck, memorizing that would be pretty rough. And then you also have cosecant, secant, and cotangent. Okay, well, so we got to memorize all that too, I guess, right? I choose to not do that personally. I just make what I need when I need it. And then there's some disadvantages to that too, because it's slower, right? Okay, if you want to go back and relearn at unit circle and like get back into memorizing all of this stuff, do a simple Google search for um, creating the unit circle, memorizing the unit circle, practicing the unit circle. If you do a Google search for any of those things, especially like practicing the unit circle, there's all kinds of online virtual apps that'll quiz you, and give you some really quick practice with that if you want to. Being fast on this on a test would be really, really helpful. Okay. Um, I think memorizing the table is ridiculous, but okay. So also you can take a complete course in trigonometry if you'd like to, if you've got a couple hours to spend. If you go to just Google Khan Academy trigonometry. There are several different parts of this Khan Academy course, and you can do any part you wanted to if you want that extra practice. Okay, I hope this was helpful. Feel free to ask me questions in class. I'm always there for you. All right.